Surface tension is property of liquids. Elasticity, all these things, basically we have solved for solid bodies. Surface tension is property of liquids, right? And it's a very common phenomenon, very common property. Due to this property, what happens? Due to this property of surface tension, the liquid free surface tries to attain the minimum surface area. Right? You have seen few examples. If I draw examples, you can see a raindrop. Raindrops. Raindrops are spherical, right? Why raindrops are spherical? Because if you see the free surface area of this liquid, it is minimum in case of a sphere. Rather, if you take the same volume of a cube or any other shape, you will find the free surface area will be more in that case, right? If you have a paintbrush, right? If you have a paintbrush and if you this dig this paintbrush inside the liquid, you will find that the bristles are moving like this. As soon as you take it outside, you will find that the bristles are coming close to each other and they will stick together. Why they are sticking together? There is no adhesive force, no glue in acting in between them. Because of the free surface area now has to decrease, right? So always this type of examples are there where liquid always tries to minimize its free surface area. This property of liquid is known as the surface tension. Why this property comes, that we will discuss. First, let us understand that surface tension is basically a property of liquid. The liquid surface behaves like a stretch elastic membrane which has a natural tendency to contract and tends to have a minimum possible area. This property is called surface tension. What is stretched elastic membrane? Stretch elastic membrane is like a balloon, right? Elastic membrane is like a balloon, right? Have you seen the a rubber balloon? All of you have seen that. If I inflate that rubber balloon, if I inflate it and I release that rubber balloon or I prick somewhere, let air to come out, you will find that always this balloon tries to attain a minimum surface area, right? It will always try to attain a minimum surface area, right? It will deflate and try to attain a minimum surface area. Why? Because in a inflated condition there is a tension acting inside the membrane. Yes or no? In inflated condition there is a tension acting inside the membrane, and due to that tension, when you release it, the membranes, the molecules of membrane, they will try to come closer in order to minimize the surface area. Liquid free surface can also be assumed as a elastic membrane, right? So if you have a flat membrane, suppose if you have a elastic membrane, a horizontal elastic membrane like this, a horizontal elastic membrane like this, and if you put some weight on this elastic membrane, you will find that the elastic membrane will come down like this, right? In this particular condition, the surface area of this elastic membrane is more than what was initially. And in this particular condition, there is a tension developed inside the elastic membrane. Yes or no? Surface tension is similar force as that of the tension. These tensions are developed inside the elastic membrane if I want to increase its surface area. So these tensions are equivalent to surface tensions. Now you can understand what is surface tension. Surface tensions are only acting on the liquid free surface if you increase the surface area. Have you got it? I will again discuss mathematical way to understand the surface tension. Why the surface tension force actually occurs? For that, we have to understand what is cohesive force. The force which acts between atoms or molecules of different substances is known as intermolecular force. This force is of two types, cohesive and adhesive. Cohesive force acting between the molecules of one type or the same substance, and adhesive force acting between the types of molecules of different substance, right? So if I have a liquid, and so the liquid to liquid interaction force will be cohesive, and if I have air and liquid, air to liquid interaction force will be adhesive. Or if I have a solid, then solid to liquid interaction force will be adhesive, but liquid to liquid interaction force will be cohesive force, right? Now, how surface tension can be described by these cohesive and adhesive forces? Let us try to understand it. Concentrate on this diagram in this right side, right? You can see that, consider this fluid particle D. This fluid particle D is surrounded by so many fluid particles, identical fluid particles. So the net force on this fluid particle becomes zero. Yes or no? And why I am talking about only this small sphere? Because the cohesive force or adhesive force, these forces are only applicable for a very short range. So only near particles to this fluid, they will apply a cohesive force to this central fluid particle. As the particles is symmetrically bounded from all the directions, so the net resultant cohesive force is zero on this particle. Suppose the radius of this sphere is c, right, or r. Radius is r. Look, if I am a distance greater than r, if I am at a depth greater than r from the liquid surface, then all the fluid particles will find a sphere which will cancel all the forces, and the net cohesive force on the particle will be zero. But what about this particle A? This particle A has only, this particle A is on the surface. So this particle A cannot get a complete sphere. This sphere is called sphere of influence. This particle A cannot get a complete sphere of influence. Rather, only the lower part of the fluids are attracting this particle in downward direction. So the net cohesive force here is in downward direction. Have you got it? Not only particle A, particle B also, for your for you can say that it does not get a complete sphere of influence, so it will have a resultant downward cohesive force. Now you can ask me one more question, that this particle, although this lower half is inside liquid, so the liquids are attracting it downward, cohesive force is there downward, but outside particles are also acting, also attracting it by adhesive force. Yes or no?
Yes, sir. Yes, sir.
So outside particles are also attracting, but here the outside particle is air, right? And during our actually it is a practical case that air to liquid adhesive force is very small. If this outside particle is not air, if the outside particles are of some other liquid or some solid material, then I cannot ignore that upward force also, right? Rather, in some cases, the adhesive force may be greater than the cohesive force. But here in this particular case, as the outside surface is air, so air to water, whenever you find a air to water interaction force, you make it zero, almost negligible air to water adhesive force. So a net downward cohesive force is acting on all the fluid particles that are lying in between a layer of free surface to the radius of the sphere of influence. Have you got it? Now, what will happen if I increase the free surface area? Suppose there are 100 balls. Let us assume this ABC particles are plastic balls. 100 plastic balls kept inside this container or jar. Out of that 100, only 20 number of plastic balls are on the surface. Now if I increase that surface area, then will the number of balls on the surface still be 20, or the number is going to rise? Will the number of ball on the surface will still be 20, or it will increase?
It will increase.
It will increase because few balls that were now at the bottom, now they will rise to the surface. Consider one such ball. Suppose is one such ball which was initially at bottom having zero force on it. Due to increase of the surface area, you are actually taking this ball from this bottommost point or anywhere inside the liquid, from this inside part to the topmost part. In doing this, as the ball is moving from depth to surface, are you doing any external work for that?
No.
Yes or no? Are we doing any external work against
No.
any force?
No, sir.
Yes, we are doing external work against that downward cohesive force. As soon as the ball will come above this level, there will be a net downward force acting on it. Yes or no?
Yes.
So by taking this ball from this surface to the topmost surface, actually some external work has to be done. If external work is done, can I say now the potential energy of the system has increased from the previous one?
Yes, sir.
As the potential energy increases, will that system be stable, or which one will be more stable? The previous one where the surface area was less, or now where you have increased the surface area?
Previous one.
Previous one. So you can say that not only why this water free surface, liquid free surface actually tries to minimize its surface area, because there is has a energy perspective in that. If you increase the free surface area, basically you are increasing the surface energy, right? In order to minimize the surface energy, the water free surface or any liquid free surface will always try to attain a minimum shape or minimum surface area. For example, you have a soap bubble, right? You have a soap bubble. So the soap bubble has a small thickness. You can see that liquids are there inside the soap bubble, this thickness, and there are suppose 1,000 number of particles on the surface. Now if you blow more air, you are doing some work, yes or no? You are blowing some air and you are doing some work. Due to your work done, what you are doing, you are actually making this layer thin. You are making this layer thinner and you are increasing this surface area. Yes or no? So from
Yes,
here to here, actually, what you have done, you have taken few water molecules which were initially inside the water in zero influence. You have taken those at the surface, increasing the surface area. You have done some that external work. Have you got it?
yes, sir.
All right. How do we mathematically define surface tension? Very simple. As we know that liquid free surface, suppose this is a liquid free surface, and how do I find surface tension? You find any imaginary line. Surface tension force is always perpendicular to that imaginary line and on the plane of the liquid surface. It should be parallel to the liquid surface, perpendicular to the imaginary line, right? So if we have a stretched membrane as I have drawn previously, that suppose this is a this is a liquid free surface, you can always assume the free surface of the liquid to be a stretch membrane, right? Now if you apply some force, downward force on it, apply some downward force on it, then you will find that the surface area increases, right? Now this is the suppose new shape of this free surface area. You have applied some force here. So if you draw a line here, then you will find that surface tension force is acting perpendicular to this line, parallel to this free surface at this point, also at this point, right? So these are the forces of surface tension. Now how do I define the surface tension? If this length is L, if this length is L, then I can say that this force is nothing but surface tension multiplied by L. So surface tension is defined as that force by unit area. Force per unit area is that surface tension, right? It is very important to understand the direction of the force, right? The direction of force is always perpendicular to any imaginary surface. Here I have taken this imaginary surface, perpendicular to that imaginary surface, and it is parallel to the liquid free surface, right? That is only written here, and the surface tension force is nothing but F by L, which is Newton per meter. But as I have told you, that surface tension can also be explained in terms of energy, right? So how do we use surface tension in terms of energy? Let us try to understand it. Suppose you have created a rectangular wire frame, right? Means you have made a wire bent in this shape, in this C shape, and you have another wire which can freely move on this surface, right? So this is a rectangular portion, and what you do, you just dip this rectangular portion in a liquid solution. Liquid solution means it will be easy to do it if you have a soap solution, right? So you will find there is a thin soap film that will be created in between this. Have you noticed it?
Yes, sir.
Yes. So a thin soap film will be created inside this area. If this this rod is movable without any friction or any other resistance force, you will find that if you release it, it will go in leftward direction so that this surface area can decrease, right? It will go in the left side direction. But what you do, you apply a very small force F, and by application of that force F, suppose you have shifted this rod, this moving rod or movable rod, by a very small displacement delta x. Right? Suppose this is the new position of the rod and you have shifted it by delta x. By delta x. If I say that this length is L and the surface tension is T of this liquid soap solution, can you tell me what is the value of force F then? If I slowly move it so that the rod always in equilibrium. So what is the value of F? From the definition of surface tension, can you tell me what is the value of F? Yes. T into L?
Yes, sir. Yes.
But if you look closely, you will find that you are only able to see this top surface of top free surface of the soap solution. Actually, there is another soap solution layer, free surface, which is lying below this top surface.
Yes. Yes, sir.
Right?
Yes,
we are not able to see from top view. In bottom, if you are just opposite side, on the opposite side, you will able to see the other surface. So actually there are two free surfaces. If this is the cross section and if you try to look on this rod, right, then you will find this like this. If this is the cross section of this rod, movable rod, this is the rod, suppose, you will see that this is the soap solution where the liquid lies. This is the soap solution. Yes or no? The liquid is lying inside this layer. This is the thickness of the soap solution. Can you see that? So whenever you have to find a free surface, consider air to water interface. So air to water interface is two interfaces are here. One is this top surface, another is this bottom surface. Both are free surface. Yes or no? So if I apply some force of surface tension, you will find the surface tension force T into L is acting on the top surface as well as it is acting on the bottom surface. So the force of surface tension is 2TL. Right? Always remember that you have to consider this force with the number of free surfaces, liquid free surface. So what is work done by this force? What is work done by this external force F? Is that force a constant or variable?
Constant. Variable.
It's a constant force. Look, if you
Sir,
yes, surface tension is constant, L is also constant. Even if you are moving in this direction, is that length changing? No, the length is not changing. Right? So what is the work done by this external force? Can I say it is 2TL into delta x only? Yes or no? Can I say that this work done by external force has only increased the surface energy of the free surface? Can I say that? Yes. So that is equal to surface tension multiplied by 2L delta x. Now what is L into delta x or what is 2 into L delta x? Is that area? Yes. Is that the increase of free surface area if you take both upper and lower segments? Yes or no? So can I say that surface energy is equal to surface tension multiplied by delta A, which is increment of free surface area. or change in free surface area, rather you can say. It can also decrease. Change in free surface area. Change in free surface area. So how the surface tension is defined? It is delta U by delta A is also definition of surface tension, joule per meter square, right? Surface energy per unit area is also surface tension. So it can be defined in both the ways. Either it is T equal to F by L, or it is delta U by delta A, right? Both the definitions of surface tension you can use.
Sir?
Bolo?
Sir, is surface tension a vector quantity or tensor quantity?
Surface tension, definitely, you cannot, it's just like a pressure thing, right? At a particular point it may have different directions, so definitely it's not a vector quantity. You can tell it is a tensor quantity, but if it is not there in your syllabus, you can just write it is a scalar quantity, right? Anything else? Have you understood the mathematical expression for surface tension? Clear this one? Okay. Now the questions are not very tough. We can easily find them. First question says a ring of mass m radius r is placed on water surface. Find the vertical force needed to pull the ring up. And if I apply an external force F, then it is not only balancing mg, but now you will find that the liquid will apply a surface tension force on this outer surface of this ring,
Yes.
right? As well as on the inner surface, the liquid will apply another surface tension force, right? So the net force should be mg plus 4 pi rt. Have you got the visualization
Sir,
here? Yes.
Yes, sir.
so will the surface tension not act in the direction parallel to the water surface?
Water surface is parallel here. Actually, when you try to move it up, then the water surface is not flat. You will find that the water surface will rise somewhere, bent something like this. Yes or no? So the surface tension will act parallel to the water surface only.
So means because of the additive force it will rise.
Yes. This water surface will rise because of the yes, adhesive force, but the surface tension you can calculate because this is the air water interface. You can easily calculate the surface tension by that property. If it were a disk, then the force would be smaller. Yes or no? If it were a
Same.
disk, then inside there will be no surface tension, only outer surface. I will find 2 pi rt.
Plus 2 pi.
Find the maximum possible mass of the greased needle floating on water surface. Suppose the length is L given. A needle which has a length L, and these are the surface tension forces actually. So what is the maximum mass possible for the greased needle to float on the surface?
Sir, 2FL cos theta by G.
Yes, for maximum mass you make cos theta to be 1.
Then it will be 2FL by G.
Yes.
2FL by G.
Yes. F means TL. F is not force, 2 into T into L. If you see that if I keep a needle, then the water surface will somehow bend like this, right? So the surface tension force will act parallel to the water surface like this. And if the length is L, then the surface tension force will be T into L. and this force is also T into L, and there will be a weight downward, right? So I can draw the free body diagram here, cross section view. You can see this is the T into L, this is the T into L, and this is weight mg. If this angle is theta, if these angles are theta, then I can say 2TL cos theta is equal to mg. So m is equal to 2TL cos theta by g, right? So is equal to m must be less than or equal to 2TL by g. Look, this is a very small mass, and if the mass is that small, particles can float on the liquid surface, not because of the buoyancy force, but because of the surface tension, right? That is why you can see few insects, they can move and they can run over the water surface.
Yes, sir.
Right? That is not because of the buoyant force, because their volumes are not that large, that because of buoyancy they can float. They float or run because of that surface tension force. All right. A water drop of radius 1 millimeter is broken into 10 power 6 identical drops. Surface tension of water is given. What is the energy spent in this process?
Sir?
Yes.
Sir, is the answer 89.60 Joule?
89 by?
89.60.
Yes, it may be. Joule.
Yes, sir. No, sir, I have taken that power wrong.
Yes. Water drop of radius 1 millimeter. So, can I say that the volume of water will remain the same? Yes. So, if I say that each and every small drops has a radius small r, then I can write 4/3 pi into capital R cube is 10 power 6 into 4/3 pi small r cube. So small r is equal to capital R divided by 100, right? Now I can say what is the change in surface area. Change in surface area. Initially it was 4 pi r square, right? So final minus initial I have to calculate. So 4 pi r square into 10 power 6 minus initially it was 4 pi capital R square. So that is 4 pi. R means capital R square by 10 power 4, right? So it is 100 minus 1. R square
Yes,
by
sir.
10 power 4, so 100 minus 1. Okay, so it is 99 into 4 pi R square. That much energy is used. That much energy I have to actually
Sir, it
supply.
is
Yes?
energy we have not found out
Yes,
yet.
a delta A into, delta A I have to multiply with surface tension. So delta U is equal to surface tension into delta A. Right now, surface tension is in dyne per centimeter.
Yes, sir.
So dyne is equal to 1 dyne is how much Newton?
10 to the power 5.
10
10 to
power
the power minus 5.
10 to the power minus 5.
I've
minus
taken plus 5, that's why.
minus 10
Minus
Minus
5.
5.
minus 5. Okay. Dyne Newton is definitely a bigger unit, so dyne will be less. Divided by centimeter means 10 power minus 2 meter, right? Into delta A is 99 into 4 pi. Now R is 1 millimeter, so 10 power minus 6 meter square, right? So I think that is Newton into meter joule. That much joule will be your answer. Just simplify it. 10 power minus 5 and minus 6. Nearly it is 10 power 2. So 10 power 2 plus 10 power 2, 10 power 4, 10 power 4, and it is 10 power minus 11. So 10 power minus 7.
Yes, sir.
10 power
10 power
minus
minus
7.
7 into 900.
Yes, 10 power minus 7 into 4 pi
Into 896.
72. 4 pi into 72. So if pi is 3 point, if I say it is 3 only, so 3 into 4 into 72, right? So 864, 870 near about, you can say, right? Into 10.
896.
Yes,
So I got near about 900.
near
Yes,
about 900.
896.
8.9 square 10 to the minus 9.
8.9, so something like 8 point something you can assume, right? It is 8 point something, so 8.9 into 10 power minus 9 joule or microjoule, you can say. Not micro, it is nanojoule, right? 8.9 into 10 power minus 9 joule. That should be the answer of this question. So look, the questions are not that difficult, but only you have to understand the concepts, remember the equations. Now it is very important, one more thing, that is excess pressure inside a liquid drop and soap bubble. Right? Excess pressure inside
Sir, 10 to the power minus 9 or 10 to the power minus 5?
10 power minus 9, I think.
I think that would be 10 to the power minus 5. 10 to the power minus 5.
10 power minus 5. Have we done any mistake? One second.
So it came 819 to 20 to the power minus 7. That means 8.9 into 20 to the power minus 5.
Achha, yes, 8.9 into 10 power minus 5. Yes. Okay. So you correct it. Excess pressure inside a liquid drop, that we will now discuss. Suppose this is a liquid drop, right? Definitely spherical in shape. This is a liquid drop. Inside liquid is there. As you can see that the liquid drop is bulging outside, right? It is bulging outside. So if outside pressure is P atmosphere, then inside pressure must be more than atmospheric pressure. Whenever a liquid surface is bulging outside, the pressure inside will be greater than outside pressure, definitely. Now, how do I find this excess pressure? In order to calculate it, let us cut that liquid uh, drop. Let us cut this liquid drop from the middle, right? Let us cut it from the middle. So if I cut it from middle, then I want to draw a free body diagram of any one of the segment. any one of the segment. Right, let us try to draw it taking the left portion, left segment. Look, in this left segment, this is a hemisphere, a solid hemisphere like thing, right? And the excess pressure delta P is inside. So this excess pressure is trying to give a right side force, a force towards left side, towards left. Yes or no? What is that force? Can you tell me what will be that force? Because the excess pressure I have assumed delta P. So which area I will multiply? I should multiply with delta P.
Sir, your projection pi r square.
It's always the projection area that I will multiply. Projection area. Right? I have also done it in several places, but even if you want to know, you can just try to understand it. That if I take any small portion here, then the force will be pi into small area, delta P into small area, delta S suppose. And similar it will be, you will find another area here where this force will be delta P into delta S. Now delta P is a constant. So if I have to find out the net force, I cannot add these two forces, rather I will add their components. Right? I will add their horizontal components actually. Right? So if I say that this angle is theta, now you will find this angle is also theta. So the net force F that I have got here as delta P into pi r square, you will find that net force is equal to integral of delta P into delta S cos theta, right? Now delta P is constant, you can take it outside, but what is delta S cos theta? If you look to this diagram, yes, this is the delta S surface area on this surface. This angle is theta, right? This angle is theta. So if I draw a perpendicular line like this, so this is the delta S, right? Then you will find that this angle will also be theta. So delta S cos theta is nothing but this area. Delta S cos theta. Yes or no? So delta S cos theta is actually the projection area of this delta S on this flat surface. Now if I add all the projections, ultimately what I will get? I will get pi r square on the flat surface only. Yes or no? Now this force is due to the excess pressure which is given by this excess pressure towards the left. But as this sphere is in equilibrium, this hemispherical part is in equilibrium, so there must be some another force which is balancing this excess pressure force. Now what is that extra force? Can you tell me?
Surface tension on the
Surface
surface.
tension force. Yes. You can see that it was a stretch membrane. Suppose this hemispherical area, you assume that it was initially a flat. Now due to this force, that area become a hemisphere. So the surface tension force will act at all the free surfaces, and here there is only one free surface available, air water interface. Yes or no?
Yes.
So what is that surface tension force? Is it 2 pi r into t?
2 pi into t. Yes.
So if I balance the forces in equilibrium, so delta P into pi r square you will find as 2 pi r into T. So delta P is equal to 2T by R. This formula you should remember. In case of a liquid drop, the excess pressure is 2T by R. Right? In case of a liquid drop, the excess pressure is 2T by R. You can also solve this question, try to solve this question, not by cutting it from middle. If I cut it from any other surface, I could also solve this question. The same question I could solve if I cut it from here. Yes or no? If I cut
Yes,
it
sir.
from here, suppose this is the portion I am looking into. So the surface tension force are acting tangential to the surfaces here. Yes or no?
Yes.
So these forces are, this surface radius is r. So this is 2 pi rt. But I will not take these forces. I will take the horizontal component of these two forces. So if this angle is theta, then this force is, the cos component of this force is balancing this force by the excess pressure. Now can you tell me what is the force by excess pressure on this curved surface?
Delta P into pi square.
Pi smaller square? Yes or no? Only the projection I will take. So can I say 2 pi r into t cos theta is equal to delta p pi r square. So delta p here you will get as 2t cos theta by r, right? But again, if you draw exact figure, this is the radius r. If this angle is theta, then this is 90 degree. I think this angle will be theta, or 90 minus theta. So this angle is theta, right?
Yes, sir.
So capital R cos theta equal to small r. If you put it, capital R cos theta equal to small r, you will find the same answer, which is 2t by r. Right? So this is not only done from cutting it by middle, you can also do it after cutting it from any other position. Right? It was inside a liquid drop. If I have to find what is excess pressure inside a soap bubble, then what should I do? Excess pressure inside a soap bubble, what will be the only change?
There will be two surfaces.
Yes. In case of soap bubble, you will find that this hemisphere, there is two free surface. There are two free surfaces instead of one. Liquid is present here. So one is 2 pi rt from here, another is 2 pi rt from there. Right? So this force delta p pi r square, delta p pi r square is balanced by 2 into 2 pi rt. Can you understand why I have written 2 into 2 pi rt? There is
Yes, sir.
one extra free surface available in case of soap bubble. So in case of soap bubble, what is the formula for excess pressure?
40 by R.
4T by R. Right. Okay. So remember these two formula. I will give you few questions regarding this one. You try them at home. In next class we will try to solve them, and we will move to capillary action and viscosity. Okay, that's all in this chapter. I think in next class we can finish that up.